On the first day of July 2025, a telescope in Chile picked up something moving through the solar system that had no business being here. It wasn't an asteroid. It wasn't a comet that formed in our neighborhood billions of years ago. It was something that had traveled an almost incomprehensible distance across interstellar space, crossing the void between star systems, spending billions of years in the cold dark between galaxies, and then arriving in our solar system on a trajectory so extreme that there was absolutely no doubt where it came from. Not from here, not from anywhere near here, from somewhere else entirely. Somewhere that, based on what scientists have now found inside it, operated under conditions so different from the ones that built our solar system that it is challenging some of the most fundamental assumptions astronomers have made about how planets and comets and the building blocks of life form across the universe. Its name is 3I Atlas. It is only the third interstellar object ever confirmed to pass through our solar system in recorded history. And what the James Webb Space Telescope found when it turned its instruments toward this visitor from another star system left researchers staring at data that didn't match anything they had ever seen before. This is the full story of what was discovered, what it means, and why the scientists who have spent careers studying comets are saying that 3I Atlas is like nothing we have ever encountered in our own solar system. To understand why 3I Atlas is so significant, you need to understand just how rare and how improbable interstellar objects passing through our solar system actually are. Space is unimaginably vast. The distance between star systems, even in a relatively densely populated region of the galaxy like the one our sun occupies, is measured in light years. The distance light travels in an entire year, moving at approximately 300,000 kilometers per second. The nearest star system to our own, Alpha Centauri, is roughly 4.2 light years away. An object traveling at the velocities typical of comets and asteroids in our solar system would take tens of thousands of years just to cross that distance. For an object from another star system to enter our solar system, it has to be moving at the high velocities of interstellar travel, speeds that reflect the dynamics of its original home system and of the galactic environment it has been moving through, and it has to cross our path close enough to be detected. The probability of that happening for any given object is extraordinarily small. And yet, it has now happened 3 times in less than a decade. The first interstellar object ever detected was Woronius Oumuamua, discovered in 2017. It was a bizarre, elongated object, cigar-shaped or perhaps flat like a pancake depending on which model you believed, that showed no outgassing, no cometary activity, and an unexplained acceleration that couldn't be accounted for by gravity alone. It was strange enough that a handful of scientists raised the possibility, which they themselves acknowledged was the most extreme explanation, that it might be artificial. The consensus settled on a natural explanation involving hydrogen or radiation pressure, but the mystery was never fully resolved because Oumuamua moved through the solar system too quickly to be thoroughly studied before it left. The second interstellar object, 2I Borisov, arrived in 2019. Unlike Oumuamua, Borisov was clearly cometary. It had a coma, it showed outgassing, it looked and behaved much like a comet from our own solar system, which was interesting in its own right because it suggested that at least some interstellar objects form through processes similar to the ones that operate in our neighborhood. Then came 3IR Atlas, and from the moment it was detected, everything about it was more extreme than its 2 predecessors. Its orbital eccentricity, the parameter that describes how dramatically hyperbolic its path through the solar system is, was measured at approximately 6, 14. For comparison, Oumuamua had an eccentricity of approximately 1, 2, and Borisov had an eccentricity of approximately 3, 37. An eccentricity of exactly 1. 0 would mean an object is moving at precisely escape velocity from the sun. It arrived from outside and will leave, but just barely. Every number above 1. 0 represents increasing excess velocity. The more hyperbolic the orbit, the faster the object was moving relative to the sun when it arrived. At an eccentricity of 6. 14. 3I Atlas has the most dynamically extreme orbit of any object ever recorded in the solar system. It was moving at approximately 60 kilometers per second relative to the sun, roughly 130,000 miles per hour, when it was discovered in early July 2025, and it was decelerating as it fell inward toward the sun on its closest approach trajectory. The speed at which 3I Atlas arrived has its own scientific implications. The velocity of an interstellar object when it enters the solar system carries information about where it came from and how long it has been traveling. Objects that formed recently, in astronomical terms, in nearby star systems will tend to arrive with lower excess velocities, reflecting the local dynamics of the solar neighborhood. Objects that formed a very long time ago, in very distant star systems, will tend to arrive with the accumulated kinematic signature of billions of years of galactic motion. The velocity of 3I Atlas suggested to researchers, even before any detailed chemical analysis was done, that this object was old. very old. And the James Webb Space Telescope's observations would eventually confirm that initial suspicion in the most striking possible terms. Webb first observed 3I Atlas on August 6, 2025, using its near-infrared spectrograph instrument, the NIR-SPEC, one of the most sensitive instruments ever built for analyzing the chemical composition of faint, distant objects, by breaking their light into its component wavelengths and identifying the specific spectral signatures of different molecules. The comet was still inbound at that point, heading toward its closest approach to the Sun, and it was already exhibiting vigorous cometary activity, a growing coma of gas and dust surrounding its nucleus, extending outward as solar energy warmed the outer layers of the comet and converted its frozen ices into gas. This outgassing was scientifically invaluable, because the gases escaping from the comet's interior were carrying the chemical fingerprint of materials that had been frozen inside it for billions of years, preserved in the cold of interstellar space, now being released for astronomers to read for the first time. What NIR-SPEC found in that August 2025 dataset was the first indication that 3I Atlas was not simply a distant analog of the comets in our own solar system. The instrument detected carbon dioxide, water ice, carbon monoxide, and carbonyl sulfide in the comet's coma. But it was the ratio of carbon dioxide to water that stopped the research team. The CO2 to water mixing ratio measured by Webb was 7.6, with a measurement uncertainty of plus or minus 0. 3, that number sits. 4, 5 standard deviations above the trend observed for long-period comets and Jupiter family comets in our solar system. To put statistical terms into plain language, a measurement that is 4. 5 standard deviations from the expected value is not a minor discrepancy or a measurement artifact. It represents a genuinely extreme outlier. The carbon dioxide content of 3I Atlas relative to its water content was so high that it placed this object in a category that essentially nothing from our own solar system occupies. Then came the December observations, and everything got even more interesting. As 3I Atlas made its closest approach to the Sun at the end of October 2025 and began moving outward again, the research team turned Webb toward it again, using a different instrument. The MIRI, the mid-infrared instrument, which operates at longer wavelengths than NIR-SPEC, and is sensitive to different molecular signatures. They observed the comet twice, on December 15th to 16th, and again on December 27th, as it was moving away from the Sun and the solar warming that had been driving its most vigorous outgassing was beginning to subside. The December dataset produced the first mid-infrared chemical fingerprint ever obtained from an interstellar object in human history. And it contained something that the August data had not shown: methane. Direct detection of methane gas in the coma, confirmed for the first time in any interstellar object ever studied. It was the first detection of methane in an interstellar visitor. The methane detection was surprising in both its presence and its timing. Methane is an extremely volatile molecule. It sublimates at very low temperatures, which means it should have been among the first materials to start out gassing as 3I Atlas warmed on its inbound journey. But it wasn't detected in the August observations, despite those observations being sensitive enough to detect it if it had been outgassing prominently. The most compelling explanation is that the methane was buried deep inside the comet, beneath layers of less volatile material, and only began releasing into the coma after the more superficial layers had been stripped away by months of solar heating during the inbound approach and perihelion passage. This depth structure, with the most volatile primordial ices buried deepest, is itself information about how the comet was built and what it has experienced over its multi-billion-year journey through interstellar space. The combination of the high carbon dioxide to water ratio, the unusual methane content, and additional measurements of the comet's isotopic composition, the specific ratios of different variants of the same elements, painted a picture that the researchers found simultaneously exciting and fundamentally challenging to interpret, using the frameworks developed for solar system comets. The Webb NIR-SPEC data captured detailed measurements of deuterium, which is heavy hydrogen, a hydrogen atom with an extra neutron in its nucleus. The ratio of deuterium to ordinary hydrogen in a comet's water is one of the most diagnostic isotopic signatures astronomers use to understand where and under what conditions the comet's ices formed. Comets in our solar system have a characteristic range of deuterium to hydrogen ratios that reflect the conditions of the solar nebula, the cloud of gas and dust from which our Sun and its planets formed approximately 4.5 billion years ago. 3I Atlas's deuterium to hydrogen ratio was approximately 30 times higher than the values measured in comets from our own solar system. 30 times. The heavy hydrogen content of this interstellar visitor was so far outside the range of anything observed in our solar system's comets that it pointed unmistakably toward a formation environment radically different from the one that produced our own cometary population. Working backward from the chemical and isotopic data, the research team arrived at a conclusion that has become one of the most discussed findings in recent astronomical history. The results, published in the peer-reviewed journal Nature in June 2026, concluded that 3I Atlas appears to be approximately 10 to 12 billion years old. 10 to 12 billion years. Our own solar system formed approximately 4.5 billion years ago, making it middle-aged in cosmic terms. 3I Atlas potentially formed more than twice as long ago, in the early universe, when the conditions across the galaxy were fundamentally different from today, when star formation was more vigorous, and the chemical environment of the early cosmos left its distinctive signature in the isotopic ratios now measured by Webb. Nearly 3 times the age of our own solar system. This is not a comet that formed next door and wandered over. This is an artifact of the early universe, a preserved sample of conditions that existed billions of years before our sun even ignited, that has been traveling through the cold dark of interstellar space for an almost incomprehensible span of time and has now arrived in our neighborhood, thawing out in the sunlight, releasing its ancient chemistry for us to read. The carbon isotope ratio added another layer to the picture. The ratio of carbon-12 to carbon-13, 2 stable isotopes of carbon that are produced in different proportions under different stellar nucleosynthesis conditions, in 3I Atlas, was measured by a separate research team using the European Southern Observatory's Very Large Telescope, complementing Webb's findings with observations of cyanide molecules in the coma. The carbon isotope ratio measured in 3I Atlas differed from the values typical of solar system comets in ways consistent with the object forming in a different galactic environment, potentially in a part of the galaxy with different stellar population characteristics and a different nucleosynthesis history than the region where our solar system formed. Stephanie Meelam of NASA Goddard, one of the co-authors of the Webb study, captured the deeper significance of this finding with particular clarity. Speaking about the prebiotic chemistry implications, she noted that so far, we know of only one place in the vast cosmos where chemical ingredients led to life: our solar system, our Earth. The analysis of interstellar objects is a major step toward learning how common, or uncommon, the conditions for the evolution of life are in the universe. That statement opens a window onto what makes 3I Atlas so profound beyond its immediate scientific novelty. The chemistry of comets matters for the origin of life question because comets are thought to have been among the delivery vehicles that brought water, organic molecules, and prebiotic chemical ingredients to the early Earth. The specific chemistry of those delivered materials, the ratios of different molecules, the isotopic signatures that reflect their formation environment, influence the chemical inventory available for life's emergence on our planet. If 3I Atlas is representative of interstellar comets from very different galactic environments, and if those comets carry chemical inventories that differ as dramatically from solar system comets as Webb's measurements suggest, then the question of whether the chemistry available for life is universal or highly environment-specific becomes an empirical question that interstellar objects like 3I Atlas can actually help answer. The comet is not just a curiosity. It is a data point in the largest question humanity has ever asked. The Hubble Space Telescope's observations of 3I Atlas added crucial information about the comet's physical properties that complemented Webb's chemical analysis. Hubble imaged the comet in July 2025, when it was approximately 365 million kilometers from Earth, capturing what was at the time the highest resolution image of the object. The nucleus of 3I Atlas, the solid body of ice and rock at the center of the coma, was estimated from Hubble's data to be relatively small, perhaps a few kilometers across, with the extensive coma of gas and dust extending outward to dimensions far larger than the nucleus itself. The rapid growth of the coma as the comet approached the sun and the vigorous outgassing rates measured by multiple telescopes suggested that the comet was releasing material very efficiently, consistent with a surface that had been frozen and preserved for billions of years and was now experiencing the warming influence of solar radiation for potentially the first time in its history. NASA's Sphere-X mission, a recently launched space telescope designed to survey the entire sky in infrared light, also observed 3I Atlas, detecting organic molecules within its coma and adding to the picture of a chemically complex object carrying a diverse suite of carbon-bearing compounds. The combination of observations from Webb, Hubble, Sphere-X, ground-based observatories including the Gemini North Telescope and the Very Large Telescope, and even ESA's JUICE spacecraft, a mission to Jupiter whose trajectory brought it into position to observe the comet in November 2025, represented the most comprehensively observed interstellar object in history. Every instrument brought a different window onto the object's properties, and together they assembled a portrait of extraordinary scientific depth. One research group that trained a very different kind of instrument at 3I Atlas was the SETI Institute's Allen Telescope Array, a radio telescope facility in California, used for the search for extraterrestrial intelligence. Shortly after 3I Atlas was discovered, a team searched for radio technosignatures from the object, artificial signals that would indicate the presence of technology rather than natural processes. No such signals were detected. The scientists involved were clear that this absence doesn't distinguish between a natural object and an artificial one. A passive artifact wouldn't necessarily emit radio waves, but the search was conducted as a matter of scientific due diligence, given the extraordinary nature of the visitor and the precedent set by the unexplained anomalies of Oumuamua. The consensus interpretation of 3I Atlas is emphatically that it is a natural comet, and its chemical properties, as revealed by Webb, are fully consistent with a natural origin in a very different stellar environment. But the fact that such searches are now standard practice when an interstellar object arrives reflects how profoundly Oumuamua changed the scientific culture around these events. 3I Atlas has now moved beyond the inner solar system and is receding outward, its outgassing diminishing as it moves away from the sun's warmth, its surface refreezing, its chemistry returning to cold preservation as it accelerates back toward the velocity it needs to escape the solar system entirely and continue its journey through interstellar space. It will not return. Its hyperbolic trajectory is a one-way pass through our neighborhood. The observations that Webb, Hubble, SphereX, and dozens of ground-based facilities gathered in the second half of 2025 and the early months of 2026 are the only observations of this object that humanity will ever have. The papers being published now, analyzing those observations, drawing out the implications for our understanding of stellar chemistry, planetary formation, and the distribution of the building blocks of life across the galaxy. These represent the complete scientific legacy of this visitor, accumulated in the months it spent in our neighborhood before disappearing back into the dark. What 3I Atlas leaves behind is not just data. It leaves a shift in perspective. Before 2017 and Oumuamua, the solar system was conceptually a closed system in the way most astronomers thought about it. The comets and asteroids were ours, formed here, evolving here, telling us about conditions here. The arrival of 3 interstellar objects in less than a decade has opened a new chapter in which the solar system is understood as embedded in a galaxy full of planetary systems, each one shedding material that occasionally crosses the vast distances between stars and arrives in our neighborhood as a sample of conditions that are otherwise completely inaccessible to study. 3I Atlas, in particular, with its extreme age, its alien chemistry, its 30 times higher deuterium content, and its CO2 to water ratio that sits 4. 5 standard deviations from anything in our solar system, has demonstrated that the diversity of planetary system environments across the galaxy is even wider than optimistic astronomers had imagined. The universe, it turns out, does not make comets only one way. The conditions that build our solar system's icy bodies, conditions that left their signature in the chemistry of our comets and that ultimately contributed to the origin of life on Earth, are not the universal template. Somewhere out there, perhaps 10 or 12 billion years ago, around a star that has long since burned out or been consumed by the galaxy's evolution, a planetary system formed under conditions so different from our own that the ices it produced have a chemical fingerprint that Webb's instruments could immediately distinguish from anything in our solar neighborhood. A piece of that ancient alien planetary system just passed through our neighborhood. We read its chemistry, we measured its age, we learned something about where and how it formed. And then it left, accelerating back toward the interstellar dark, carrying the secrets of an ancient stellar system that no human instrument will ever reach, in a direction that no human spacecraft will ever follow. That is what the James Webb Space Telescope found when it looked at 3I Atlas. Not a threat, not a danger, something more quietly astonishing than either of those things. A message from the early universe, written in ice and chemistry, that traveled 10 billion years to reach us, spent a few months warming in our sun, and left us with questions about the universe that will take a generation to fully answer.